Okay, so we're almost ready to actually begin applying the laws of thermodynamics to systems to describe their properties and how those properties change over time, which is the whole point of what we're doing to start off this course. However, before we do that, I want to remind you of a really basic concept, but it actually is going to serve as the basis and going to be useful as a starting point for using and applying the energy and entropy balances. So I want to remind you of the idea of a balance in general. What does that mean? It means that any quantity in general can be balanced by thinking about a system in the following way. Whatever quantity you're talking about, we can imagine that the accumulation of that quantity, and to make this even simpler, you can even think of money in a bank or the number of cars in a parking lot or whatever you really want, whatever quantity you want to think of in some system. The accumulation of that quantity should be equal to however much is input into the system minus however much is taken out or output out of the system plus the amount that's generated within the system itself minus the amount that's consumed. Right, so the amount of money in a bank that's accumulating would be equal to the amount of money that people are depositing into the bank minus the amount of money being taken out of the bank by whoever. And then, of course, money, unless you're talking about the Federal Reserve or something, money is really not generated or consumed. But maybe at the Federal Reserve, where they're actually printing money, you could say money would be accumulating in that building because they're printing it. And I think they also, when bills get really old, they actually take them out of circulation. So in that way, money could also be consumed in a certain place. Now, before we apply this to energy and entropy, let's also apply it to a little bit more of a thermodynamics problem, but a simple one, and that is a mass balance. So for mass, unless you're talking about a nuclear reaction, mass should never be generated or consumed. So right away, this general balance, saying that accumulation is equal to input minus output, plus the amount of something that's generated minus the amount that's consumed. For mass, we can take out the last two terms because mass is never generated or consumed in chemical reactions in general. Again, we're not going to talk about nuclear reactions right now. So that may look really simple, and it is. And then to kind of put it in a more mathematical language, in a language that fits with our notation that we covered a couple lectures ago, we could write something more fancy like the following. The derivative of mass with respect to time in our system, in other words, the amount that the mass of a system is changing, is simply equal to the inputs minus the outputs. And so we can just rewrite that as the sum of all the masses flowing into and out of our system, knowing that our masses will be positive when they're flowing into a system, and knowing that they'll be negative when they're flowing out of the system. And then you could also, for example, integrate this equation with respect to time, and if the mass flow rates were constant, it would obviously be super easy to integrate, and that would just tell us, for example, that the change in mass is equal to the masses put into the system minus the masses taken out of the system. So we just integrated the m dots with respect to time. And again, if that's a constant, it would just be, for example, the kilograms per second flowing into or out of the system times the amount of time. That would give you the total mass put in or taken out of the system. So the change in mass, again, the accumulation of the system of its mass, would be equal to the amount of mass put in minus the amount of mass taken out. So this looks kind of fancy, even with this really simple idea, but of course it's really simple. Let's go ahead and take a look at an example.